Let's look at the kinds of parallelism that are available, first of all from the point of view of the architecture. The simplest kind of instruction level parallelism is pipelining. Instructions move the stage through the stages of the pipeline one after another. So you see the first one starts at the first cycle, the next one starts at the next cycle, and these stages mean instruction fetch, instruction decode, execute the instruction, perform any memory operation that's necessary, and then write back the result to, let's say, a register. And this is called a classical five-stage pipeline. If you haven't seen it before, it can be overlapped in the way that you have one instruction per cycle starting, and then each instruction is using different functional units at the same time so they don't collide. So that's very simple pipelining. The next kind of pipeline, or the next kind of parallelism is superscalar or VLIW. VLIW stands for Very Long Instruction Word. A single instruction is 256 or more bytes long. Let's suppose that we have these four instructions. Both of the loads can be done at the same time. As soon as the load is completed, the corresponding add can be started. So in VLIW, the compiler figures out that the loads can execute at the same time, and then it does the adds. It compiles the loads into the first instruction, which, because it's 256 or more bytes long, has room to specify both of those operations and all of the operands, and then it compiles the adds into the second instruction. In a superscalar, by contrast, this is VLIW, where things are figured out at compile time. In a superscalar, by contrast, the architecture figures this out at runtime by checking for dependencies dynamically between instructions. Both of these techniques can execute several instructions in parallel, which amounts to a modest degree of parallelism. But for superscalars, fast communication is required at the register level to compute the dependencies. VLIWs, by contrast, do that with a compiler, so you need a more complicated compiler, and the compiler might reorganize some programs to work in the new environment, or the programmer might need to be called in. But everything is done at compile time, so you can get by with a simpler architecture. Now, ILP, as we noted, is slowing. The first reason is because remember the pipeline that I showed you a few slides ago? Let's look at that. So as long as an instruction starts the cycle after the previous instruction, all is cool. But if there's a branch instruction, then all of the work that we've done, let's say we encounter a branch right here, all of the work we've done in subsequent instructions needs to be thrown away, and we need to start fetching at the branch address, rather if it's a taken branch, rather than at the current program counter location. So that means that whenever you have a branch, it induces what's known as a pipeline break. Now, in order to accommodate this, modern architectures have ways of predicting branches. Let's say you're in a loop and you've executed the loop 905 times so far. On the 906th time, the architecture is going to guess that you're going to branch back to the loop. So it's going to start prefetching instructions at the loop target rather than at the next sequential instruction, and then you won't have that pipeline break. But branch prediction accuracy is already over 90%, and it's hard to make it 100%. You can get very small incremental improvements, so you can't have more instructions executing in parallel if they're constrained by branches. Secondly, there's the number of pipeline stages. Now you could, up to a point, get more parallelism by adding more pipeline stages for each instruction. But when you get to 20 to 30 of them, well then the time it takes to latch the values in the latches in between stages gets to be really significant. And also, the operands that depend upon other things being computed, you still have to wait for that, and you still have to wait for memory. so it doesn't really help you that much. Then processor width is already high, in other words, superscalar. You've got maybe dual issue or quadratic issue or something like that. And you can't really get any farther because if you go past quad issue, then you quadratically increase the complexity. And as far as cache size is concerned, you could increase the size of a cache, but it takes up chip space, so you have to trade that off against other things you could do with that chip real estate. And in general, if you want to reduce the miss rate by half, you need to at least double, and often more than double, the cache size. So you really can't improve instruction level parallelism by getting more into the cache either. Well, current trends are that you have 4 or 8 core multiprocessors or multi-core processors, and of course they're connected together into larger multiprocessors. There are certainly processors with more cores than that, but probably not with quite so much market share. Clock frequencies are given there, 2 to 3 gigahertz range. You've got superscalars, and you've got two-issue SIMD, where you're issuing two instructions at the same time, and the instructions can operate on multiple data items. We'll talk a little bit more about that later. The caches, well, you see how the caches are organized there, and the chip power is in the range of 100 watts. So I'd like to pause again and have you browse the web or the textbook for information on more recent processors and fill out the form. And we'll continue in a moment. Now we've just talked about parallelism from an architecture point of view. I'd like to talk about it now from a programming point of view. We'll talk about loop level parallelism, task level parallelism, and programming level parallelism. So to start off with, we have loop level parallelism. Sometimes each iteration of a loop can be performed independently. Think about adding two vectors, each of which resides in an array. Well, you can certainly add the first element of an array at the same time that you add the second elements of the corresponding arrays, etc. So you can perform this loop. Independent, or each iteration independently, and that means that if you have multiple processors, each one can work on an iteration of a loop without contacting the other processor until it's done with the iteration. Sometimes iterations, though, cannot be performed independently because there's no loop level parallelism. So you see here, you're taking a sub I minus 1 and adding it into the new sum of ai. And so if you didn't already have a sub I minus 1 computed, you couldn't start computing a sub I, so you've got a loop dependency there, and that makes it that limits the amount of parallelism you can get. Now, an advantage of loop level parallelism is that you can get very high parallelism. More than 1,000 loop elements can execute at the same time if you have the proper kind of parallel processor. And it's often easy to achieve load balance. If you've got 1,024 processors working on elements of your array, well, they're all busy as long as each other, and then you just move to the next 1,024 and you've got very good load balance. But some loops do not parallelize, as we just saw. There are other ways to parallelize it, but they don't parallelize in an obvious way, and they don't parallelize with that degree of parallelism. And also, some applications don't have many loops. Think about a search application, for example. Everything depends upon the previous iteration. If you're using a loop, and so you can't get very much parallelism. And well, there's some apps that have linear code, although there aren't very many. Most of them have branches every 4 or so instructions. So if you've got the kinds of loops that can be parallelized where the data is known in advance, you're in good shape. The next kind of parallelism is task level parallelism, where you have, well, two processors could each execute one loop, or, as we see over here, you break up a loop so the first processor computes the first loop, second processor computes the second loop, Or you could also break it up so two processors each execute one subroutine. And then, maybe you add the values together at the end. But you're still using two processors, except they're running completely different code in both of those cases. Examples of this would be thread-based applications like editors, where you have spell checking and visual display going on while you have editing. So what's the advantage of this? You get larger granularity to your parallel items, which means lower communication overheads, but you don't get that much parallelism, and it's also hard to balance. Where we saw the sum and product loop, depending upon your architecture, they may take similar amounts of time. But if you've got the different subroutines executing on different processors, there's no particular reason that you should believe that they're going to take the same amount of time. So the last level of parallelism I want to talk about is program level parallelism. And my favorite example of this, and actually practically the only one that's easy to understand, is parallel make, where you have the compiler work on compiling different modules of the program in parallel, and then when you're done, you link them all together. So this is you get a lot of you get parallelism for as many files as you have you're compiling, and an advantage of this is you don't have to communicate between the different programs till you're all done, so you don't get any slowdown from synchronization. But it's also hard to balance this code. Some routines take longer to compile than others. And you better be doing parallel make or something like it, because not very many applications work that way.